What if I told you that right now, at this very moment, the universe is conspiring to trap you? Not in some philosophical sense, but in a very real, physical way. You're sitting there, watching this video, and you might think you could theoretically travel anywhere in the cosmos if you just had enough fuel, enough time, enough technology. But here's the shocking truth that even the brightest minds in history struggled to accept. There is a wall, an absolute, unbreakable cosmic speed limit built into the very fabric of reality itself. And that limit is the speed of light, 299,792,458 meters per second. But here's what will absolutely shatter your understanding of the universe. Light doesn't travel at the speed of light because it's fast. Light travels at the speed of light because that's the speed of causality itself, the maximum rate at which cause and effect can propagate through the universe. The speed of light isn't about light at all. It's the speed of reality. Think about that for a second. When Einstein discovered this in 1905, he didn't just find a speed limit for moving objects. He discovered that the universe has a fundamental speed limit for information, for cause and effect, for everything that can possibly happen. And the implications are so mind-bending, so reality-warping, that over the next few hours, I'm going to take you on a journey that will fundamentally change how you see space, time, and your place in the cosmos. Before we dive deep into this rabbit hole, do me a favor, hit that like button and subscribe, because what you're about to learn will challenge everything you thought you knew about reality. And I'm curious, where in the world are you watching this from? And what time is it there? Drop a comment below. It blows my mind to think that while you're watching this, the light from your screen is traveling to your eyes at the absolute speed limit of the universe. And by the time you finish this video, you'll understand why that's one of the most profound facts in all of existence. Now, let's start unraveling this cosmic mystery. For most of human history, we thought speed was unlimited. If you had a fast enough horse, a better engine, stronger legs, you could just keep going faster and faster. The ancient Greeks debated whether light traveled instantaneously or had a speed at all. Aristotle argued that light had no speed. It was simply the presence of transparency. This idea dominated thinking for nearly 2,000 years. The first person to seriously challenge this was a Danish astronomer named Ole Rachmer in 1676. He wasn't trying to measure the speed of light directly. He was studying Jupiter's moon Io, tracking its eclipses as it disappeared behind the giant planet. But Rachmer noticed something strange. The timing of these eclipses changed depending on where Earth was in its orbit. When Earth was moving toward Jupiter, the eclipses happened earlier than predicted. When Earth was moving away, they happened later. Here's the revelation that changed everything. Rachmer realized that light took time to travel. The eclipses weren't actually happening at different times. The light carrying information about them was taking longer to reach Earth when we were farther away. Using the diameter of Earth's orbit and the timing differences, Rachmer calculated that light traveled at about 220,000 kilometers per second. Not perfectly accurate by modern standards, but astronomically close for someone working in the 17th century with telescopes that would be considered toys today. But here's what most people don't realize. Even after Rachmer proved light had a speed, scientists still thought you could exceed it. They imagined you could theoretically build a ship that went faster than light, just like you could build a ship that went faster than sound. The speed of light was just another number, another barrier to overcome with better engineering. Everything changed in the late 1800s when physicists started playing with electricity and magnetism. James Clerk Maxwell, a Scottish physicist working in the 1860s, was trying to unify the equations describing electric and magnetic fields. He discovered something absolutely bizarre hidden in the mathematics. When he combined the equations, they produced a wave equation, but this wave traveled at a specific speed that fell out of the math naturally. That speed was 299,792 kilometers per second. Maxwell had discovered that light was an electromagnetic wave, and its speed was hard-coded into the fundamental constants of nature. But here's the part that should make your hair stand on end. Maxwell's equations gave you the speed of light, but they didn't tell you relative to what. Speed is usually measured relative to something else. A car going 60 miles per hour is moving relative to the road. Sound travels at 343 meters per second relative to the air. But the speed of light in Maxwell's equations was just ... a number, an absolute, not relative to anything. This created a massive problem. According to Newtonian physics, if you were moving toward a light beam, you should measure it going faster. If you were moving away from it, slower. Just like running toward a thrown ball makes it approach you faster. But Maxwell's equations suggested light always traveled at the same speed, no matter how you were moving. This seemed to violate basic common sense. Scientists were so disturbed by this that they invented an invisible substance called the luminiferous ether, an undetectable medium filling all of space that light waves traveled through. Problem solved, right? Light traveled at a constant speed relative to the ether, just like sound travels at a constant speed relative to air. But then came one of the most important failed experiments in scientific history. In 1887, two American physicists, Albert Michelson and Edward Morley, set up an incredibly precise apparatus to detect Earth's motion through this ether. The logic was simple. As Earth orbits the Sun, we should be moving through the ether at different speeds in different directions. Light should appear to travel at slightly different speeds depending on which direction we measure. They built an interferometer, a device that split a light beam, sent the halves in perpendicular directions, then recombined them. If the ether existed, the light beams would take slightly different times to complete their journeys, creating an interference pattern that would shift as the apparatus rotated. Michelson was so confident they'd detect the ether that he called it a practicable method of finding the motion of the Earth relative to the ether. The result? Nothing. Zero. No matter which direction they pointed their apparatus, no matter what time of day or year, light traveled at exactly the same speed. It was as if the universe was playing a cosmic joke. How could light have a constant speed regardless of the observer's motion? That violated everything physics knew about relative motion. This is where our story gets truly strange, because the real answer was so counterintuitive that it took a 26-year-old patent clerk working alone in Switzerland to figure it out. And what he discovered didn't just explain the Michelson-Morley experiment. It revealed that space and time themselves are not what we think they are. But before we get to Einstein and the revolution he sparked, I need to plant a seed in your mind that's going to grow into something extraordinary. That weird constancy of light speed? It's not a property of light. It's a property of space-time itself. Light just happens to travel at the universe's speed limit, but that limit exists even without light. It's the cosmic speed limit for information, for causality, for the very possibility of things affecting other things. Now, are you ready to find out why nothing can break this limit? Because the answer is going to require us to completely reimagine what space and time actually are. Let's talk about trains. I know that sounds mundane, but stay with me because this is where your understanding of reality is about to fracture. Imagine you're standing on a train platform. A train passes by at 50 kilometers per hour, and someone on the train throws a ball forward at 20 kilometers per hour relative to the train. How fast is the ball moving relative to you on the platform? Easy 70 kilometers per hour. You just add the speeds. This is called Galilean relativity, and it's been common sense since Newton. Now imagine that instead of throwing a ball, someone on the train turns on a flashlight, sending light forward. The light travels at 299,792 kilometers per second relative to the train. The train is moving at, let's say, 100 kilometers per second relative to you. So how fast is the light moving relative to you on the platform? According to common sense and Newtonian physics, it should be 299,892 kilometers per second. Just add the speeds like we did with the ball. But according to actual measurements, according to the Michelson-Morley experiment, according to every experiment ever performed, the light is traveling at exactly 299,792 kilometers per second relative to you. The exact same speed as it was relative to the train. This is not a small discrepancy. This is reality breaking the fundamental rules we thought governed motion. And here's what Albert Einstein realized in 1905. We were asking the wrong question. The question isn't, why does light always travel at the same speed? The question is, what does it mean for space and time if light always travels at the same speed? Einstein's answer, published in his paper on the electrodynamics of moving bodies, was revolutionary. Space and time are not fixed, absolute things. They're flexible, relative, interconnected. What we call space and what we call time are actually aspects of a single entity spacetime. And here's the mind-breaking part. Time passes at different rates for different observers, depending on how fast they're moving. Think of it like this. Imagine the universe has a fixed speed limit, call it c. Everything travels through spacetime at the same total speed c. But you can divide your motion between moving through space and moving through time. When you're sitting still, all your motion is through time. You're aging at the maximum rate. When you start moving through space, some of your motion through spacetime gets diverted into spatial motion, which means you have less motion left over for moving through time. You age more slowly. This isn't science fiction. This is experimentally verified reality. In 1971, physicists Joseph Haffel and Richard Keating took atomic clocks on commercial flights around the world. When they compared these clocks to identical ones left on the ground, the flying clocks had lost time. They had aged less than the stationary clocks, by exactly the amount Einstein's equations predicted. The difference was only a few hundred nanoseconds, but it was there, measurable, real. But here's what absolutely blows my mind about this. It means that right now, your head is aging faster than your feet. Yes, really. Your feet are moving through Earth's gravitational field and experiencing time dilation. Your head, being farther from Earth's center, experiences time at a very slightly faster rate. The difference is about 90 nanoseconds per day. GPS satellites have to account for this, or they'd become inaccurate within minutes. Now, let's get back to our speed limit. If time slows down as you move faster, what happens as you approach the speed of light? According to Einstein's equations, as your velocity approaches the speed of light, time dilation approaches infinity. From the perspective of someone watching you, time on your spaceship would appear to almost stop. But here's the really weird part. From your perspective on the spaceship, time feels normal. It's time in the outside universe that appears to speed up. This is called time dilation, and it's just one half of Einstein's special relativity. The other half is equally bizarre, length contraction. As you move faster, distances in your direction of motion shrink from your perspective. If you could travel at 99% the speed of light, distances would compress to about 14% of their stationary length. At 99.99% the speed of light, they'd shrink to about 1.4%. Think about what this means. Imagine you're in a spaceship accelerating toward a star 10 light years away. From Earth's perspective, even if you traveled at 99.99% the speed of light, the journey would take a little over 10 years. But from your perspective in the spaceship, because of length contraction, the distance to the star would appear to be only about 0.14 light years. With time dilation in effect, your clock might measure the journey as taking only a few months. This is not theoretical. This happens with subatomic particles every day. Muons are unstable particles created when cosmic rays hit Earth's upper atmosphere. They decay with a half-life of 2.2 microseconds. At that lifetime, even traveling at near light speed, muons shouldn't be able to travel more than about 660 meters before decaying. But we detect them at sea level after they've traveled over 10 kilometers through the atmosphere. How? Time dilation. From the muon's perspective, it only lives for 2.2 microseconds. But from Earth's perspective, because the muon is moving so fast, time has slowed down for it. It lives long enough to reach the ground. From the muon's perspective, the atmosphere is length contracted, so it doesn't have as far to travel. Both perspectives are equally valid. Reality itself has become observer-dependent. Here's where things get truly mind-bending. If you could somehow accelerate to the speed of light, and we'll talk about why you can't in a moment, time would stop entirely from your perspective. The distance to your destination would contract to zero. From your point of view, you would arrive instantaneously, regardless of how far away your destination was. The entire journey would take zero time. This is why photons, particles of light, don't experience time. From a photon's perspective, if it even makes sense to talk about a photon's perspective, the moment it's emitted from a star and the moment it's absorbed by your eye occur at the same instant, even if billions of years pass from our perspective. A photon that left the edge of the observable universe 13.8 billion years ago experienced no time during its journey. But here's the question that should be burning in your mind. If getting to light speed means time stops and distances shrink to zero, making any journey instantaneous, why can't we just accelerate to light speed? Why is there a cosmic speed limit at all? The answer lies in something Einstein discovered that's even more shocking than time dilation and length contraction. And this is where we start to understand why the speed of light isn't just a speed limit, it's a fundamental property of the universe itself, woven into the very structure of existence. Are you ready to have your mind completely blown? Let's talk about energy. You probably learned in school that kinetic energy, the energy of motion, equals 1/2 times mass times velocity squared. So if you double an object's speed, you quadruple its kinetic energy. Simple, right? But here's the problem. That equation is wrong. Or rather, it's an approximation that only works at low speeds. The real equation, the one that emerges from Einstein's special relativity, is far more disturbing. As you accelerate an object, you add energy to it. That energy has to go somewhere. At low speeds, it goes almost entirely into increasing the object's velocity, just like the classical equation predicts. But as you approach the speed of light, something bizarre happens. The energy starts going into the object's mass instead. Yes, you read that right. As an object moves faster, it gets heavier. This is called relativistic mass increase, and it's a direct consequence of Einstein's famous equation, E equals mc. Energy and mass are equivalent. They're the same thing in different forms. When you add kinetic energy to an object, you're adding to its mass energy, and at high speeds, this manifests as an increase in mass. Here's the mathematical reality. As your velocity approaches the speed of light, your mass approaches infinity. And here's where the cosmic trap snaps shut. To accelerate an object of infinite mass requires infinite energy. It's not just that we don't have enough energy to accelerate something to light speed. It's that no amount of energy in the entire universe would be sufficient. The speed of light isn't a speed limit because it's really fast. It's a speed limit because the universe's laws make it mathematically impossible to reach if you have mass. Let me give you some numbers to really drive this home. Let's say you want to accelerate a 1,000 kilogram spaceship about the mass of a small car, the various fractions of light speed. To reach 90% of light speed, you'd need about 1.3 times 10 joules of energy. That's roughly the total energy consumption of the entire United States for 3 years. To reach 99% of light speed, you'd need about 5.6 times 10 joules more than 10 times as much. To reach 99.9% of light speed, you'd need about 1.6 times 10 joules more then double the previous amount. To reach 99.99%, about 510 joules. Do you see the pattern? Every time you want to get closer to light speed, the energy requirements don't just increase, they increase exponentially. Each additional 9 in your percentage requires more energy than all the previous acceleration combined. It's like climbing a mountain that gets steeper with every step, until the final inch of height becomes an infinite vertical wall. At exactly the speed of light, the energy required becomes infinite. Not really large, not more than exists in the universe. Infinite, undefined, mathematically impossible. This is why photons can travel at light speed, but you can't. Photons have zero rest mass. For massless particles, traveling at light speed doesn't require infinite energy. It's the only speed they can travel at. They're born moving at light speed and can never slow down. An electron, on the other hand, has mass tiny, but not zero, and thus can never reach light speed, no matter how much energy you pump into it. But here's what really makes this concept mind-bending. This isn't a limitation of our technology or our engineering. This is a fundamental law of the universe. Even a civilization a billion years more advanced than us, with technology we can't even imagine, could not accelerate a massive object to light speed. They would run into the exact same mathematical impossibility we do. The speed of light is not a wall we haven't figured out how to break through yet. It's the edge of what's physically possible. It's like asking what's north of the North Pole. The question itself doesn't make sense. Now, some of you might be thinking, wait, I've heard about particles that travel faster than light. What about tachyons? Here's the truth about tachyons. They're hypothetical particles that, if they exist, would always travel faster than light and could never slow down to light speed or below. They're a mathematical curiosity that emerges from special relativity, but there's never been any experimental evidence for them. More importantly, even if they existed, they wouldn't violate the cosmic speed limit. They'd exist in a weird region of physics where cause and effect become scrambled. And here's why faster-than-light travel creates problems that go far beyond just needing a lot of energy. It breaks causality. It makes time travel possible. And not in a fun science fiction way. This creates logical paradoxes that make the universe impossible way. Let me explain. In special relativity, different observers moving at different speeds disagree about whether two events happen at the same time. This is called the relativity of simultaneity. Two events that appear simultaneous to you might appear to happen at different times to someone moving relative to you. Usually, this is fine. It's just a quirk of spacetime. But if you could send information faster than light, here's what becomes possible. Imagine you send a faster-than-light message to a spaceship moving relative to Earth. Due to the relativity of simultaneity, from the spaceship's perspective, your message arrives before you sent it. If they immediately send a faster-than-light reply back to you, that reply could arrive on Earth before you sent the original message. You've just received a message from your future self, creating a causal loop of time travel paradox. This isn't science fiction hand-waving. This is what the mathematics of special relativity tells us. Faster-than-light travel doesn't just violate the speed limit, it violates causality itself. It makes it possible for effects to precede their causes, for you to receive the answer to a question before you ask it, for you to potentially kill your grandfather before your father is born. The universe seems to prevent this. The speed of light isn't just the fastest speed, it's the speed of causality itself. It's the maximum rate at which cause can propagate to effect. When you flip a light switch, the electrical signal travels at near light speed to the bulb. When the bulb lights up, photons leave it at light speed. Your eye receives those photons at light speed, and the electrochemical signals in your brain travel at a fraction of light speed. Every single causal chain in the universe is limited by the speed of light. Here's a way to think about it that might help. The speed of light is like the frame rate of reality. It's the maximum speed at which information can update from one place to another. Below this speed, cause and effect work normally. At this speed, you're at the edge of causality. Beyond this speed, you'd be traveling backward in time from some reference frames, breaking the forward flow of causality. But we're just getting started with the implications of this speed limit. Because when you combine special relativity with gravity, something even more profound emerges. Einstein spent 10 years after his 1905 paper trying to figure out how gravity fit into this new relativistic picture of the universe. The answer he found, general relativity, revealed that the speed of light limit has consequences that reach far beyond just how fast things can move. And one of those consequences is that the universe has trapped us in a prison of cosmic proportions. A prison so vast that most of the universe will forever be beyond our reach, even if we could somehow travel at 99.9999% of light speed. Are you ready to discover just how trapped we really are? Let me show you the cosmic cage that holds us. Right now, you're sitting in a prison. The walls of this prison are expanding outward at an accelerating rate, and the vast majority of what lies beyond these walls is already unreachable. Not just difficult to reach, but fundamentally, physically impossible to ever visit, even if you could travel at nearly the speed of light. This prison is called the observable universe, and its walls are defined by the speed of light. Here's the setup. The universe is approximately 13.8 billion years old. Light has had 13.8 billion years to travel since the Big Bang. So logically, you might think the observable universe, the region of space from which light has had time to reach us, would be a sphere about 13.8 billion light years in radius, right? Wrong. The observable universe is actually about 46.5 billion light years in radius. How is that possible? How can we see light from objects that are farther away than light could have traveled in the age of the universe? The answer reveals something profound about the nature of space itself. Space can expand faster than light. This doesn't violate relativity, because nothing is moving through space faster than light. Space itself is expanding, carrying distant galaxies with it. It's like if you drew two dots on a balloon and then inflated the balloon. The dots aren't moving across the balloon's surface, but they're getting farther apart as the space between them expands. This expansion was discovered by Edwin Hubble in 1929. He measured the distances to various galaxies and their velocities by looking at the redshift of their light, the stretching of light waves due to the expansion of space. He found that the farther away a galaxy was, the faster it was receding from us. The universe wasn't static, it was expanding. But here's where things get truly disturbing. The expansion is accelerating. This was discovered in 1998 by two independent teams of astronomers, Saul Perlmutter, Brian Schmidt, and Adam Rees, who were awarded the Nobel Prize in Physics in 2011 for this discovery. They were studying distant supernovae, exploding stars that serve as cosmic distance markers, and found that distant galaxies weren't just moving away from us. They were moving away faster than they should be if the universe's expansion was slowing down due to gravity. Something is driving the expansion to accelerate, and we call this something dark energy. We don't know what it is. It's one of the biggest mysteries in physics, but we know what it does. It makes space expand faster and faster. And here's the cosmic trap. Because of this accelerating expansion, there's a distance called the cosmic event horizon, beyond which galaxies are receding from us faster than light. Not moving through space faster than light, remember, that's impossible, but being carried away by the expansion of space itself, faster than light, can cross the expanding space between us. Currently, any galaxy more than about 16 billion light-years away is beyond our cosmic event horizon. We can still see some of these galaxies because we're seeing light they emitted billions of years ago when they were closer to us. But if you tried to travel to one of these galaxies, even at 99.9999999%, the speed of light, you would never reach it. Space is expanding between you and your destination faster than you can cross it. It's like trying to swim across a river where the current is flowing faster than you can swim. You just get swept backward. And it gets worse. As dark energy continues to accelerate the universe's expansion, more and more galaxies will cross beyond our cosmic event horizon. Eventually, every galaxy outside our local group, the small cluster of galaxies gravitationally bound together that includes the Milky Way and Andromeda, will be beyond reach. In about 150 billion years, any astronomers in the Milky Way will look out into the universe and see almost nothing, just the handful of galaxies in the local group, surrounded by darkness. The rest of the universe will have receded beyond the cosmic horizon, and the light from those galaxies will be stretched by expansion until it's redshifted into nothingness. Those future astronomers won't even know there was a Big Bang or that the universe is expanding. All the evidence will have literally sailed beyond the horizon of visibility. They'll live in what appears to be a static universe consisting of just a few galaxies surrounded by endless void. This means we're living in a special time in cosmic history, a brief window when we can still observe the deep history of the universe and the vast cosmic web of galaxies. We're lucky enough to exist when evidence of the Big Bang, the cosmic microwave background radiation, and the large-scale structure of the universe are still visible. But here's what keeps me up at night. How much has already slipped beyond our horizon? How much of the universe has expanded away from us so quickly that its light will never reach us? The observable universe, that 46.5 billion light-year radius sphere, is just a tiny bubble of what actually exists. The full universe could be infinite, or it could be mind-bogglingly larger than what we can see. There could be regions with entirely different physical laws, other intelligent civilizations, structures and phenomena we can't even imagine, all forever beyond our reach, because the speed of light, the cosmic speed limit, combined with the expansion of space, has sealed them away. The speed of light doesn't just limit how fast we can travel, it limits what we can know. It defines a cosmic horizon beyond which information cannot reach us. We're trapped not just physically, but epistemologically trapped by the fundamental structure of spacetime itself. Now, you might be wondering, if space can expand faster than light, why can't we use that as a loophole? Why can't we ride an expanding bubble of space to exceed the speed of light? This is actually not as crazy as it sounds. In 1994, a physicist named Miguel Alcubierre proposed a solution to Einstein's field equations that does exactly this. The Alcubierre drive, as it's called, would work by contracting space in front of a spaceship and expanding space behind it, creating a warp bubble that carries the ship along at effectively faster than light speeds, while the ship itself remains stationary within the bubble. Sounds perfect, right? A legitimate loophole in the cosmic speed limit? Not so fast. The Alcubierre drive has some rather significant problems. First, it would require negative energy, a kind of energy with negative mass that would repel rather than attract gravitationally. We've observed some quantum effects that might qualify as negative energy, like the Casimir effect. But harnessing enough negative energy to warp space around a spaceship is so far beyond our current technology that it's hard to even imagine how it could be done. Second, and more fundamentally, recent analyses suggest that the Alcubierre drive might violate the same causality principles that prevent faster-than-light travel in the first place. You might be able to create the warp bubble, but you wouldn't be able to control it from inside. You'd need to set up the space warping infrastructure along your route before you traveled, which defeats the purpose. The universe seems to have closed every possible loophole. The speed of light isn't just a limit on motion through space. It's a fundamental constraint on reality itself. And every time we think we've found a way around it, we discover that the universe has already thought of that and blocked it off. But here's what's truly profound about all of this. the speed of light limit doesn't just constrain what we can do, it shapes what we can be. The fact that cause and effect propagate at a finite speed means that the universe has a kind of built-in information processing rate. Reality itself has a maximum clock speed. And this raises a question that's going to lead us into some very deep territory. If the speed of light is the ultimate speed limit of the universe, what does that tell us about the nature of reality itself? Why does this limit exist? What would a universe without a speed limit look like? And could it even exist? These aren't just philosophical questions. The answers touch on the deepest mysteries of physics, from the nature of time to the possibility that we're living in something like a simulation. And to explore these questions, we need to dive even deeper into what light actually is and why its speed is so special. Are you ready to go even further down the rabbit hole? Let's talk about what makes light so special that it gets to travel at the cosmic speed limit while everything else is stuck going slower. Here's a question that probably seems simple, but has a surprisingly deep answer. Why does light travel at the speed of light? Or to put it another way, what is light? You probably learned in school that light is a wave, an electromagnetic wave specifically. But here's something that might surprise you. Light is also a particle. Or more precisely, light exhibits both wave-like and particle-like properties, depending on how you observe it. This is called wave-particle duality, and it's one of the strangest features of quantum mechanics. When light behaves as a particle, we call these particles photons. And photons have a very special property. They have zero rest mass. This is crucial. In special relativity, anything with zero rest mass must travel at the speed of light. It has no choice. Photons don't accelerate from zero to light speed when they're created. They're created already moving at light speed, and they continue at that speed until they're absorbed. But here's something even stranger. While photons have zero rest mass, they do carry energy and momentum. How can something with no mass carry momentum? Because in relativity, momentum isn't just mass times velocity. For a photon, momentum equals energy divided by the speed of light. So even though a photon has no mass, its energy gives it momentum, which is why light can push on things. This is called radiation pressure. And it's the principle behind solar sails that could theoretically propel spacecraft using only sunlight. Now here's where things get really interesting. Photons aren't the only massless particles that travel at light speed. There are others. Gluons, which carry the strong nuclear force that holds atomic nuclei together, are also massless and travel at light speed. Gravitons, if they exist, we haven't detected them yet, but they're predicted by most theories of quantum gravity, would also be massless and travel at light speed. What do these particles have in common? They're all force carriers. Photons carry the electromagnetic force. Gluons carry the strong force. Gravitons would carry the gravitational force. These particles are how forces work in quantum field theory. Forces are transmitted by the exchange of force-carrying particles. And here's the profound implication. The speed of light isn't really about light at all. It's the speed of causality, the maximum rate at which forces can act, at which information can propagate, at which cause can produce effect. We call it the speed of light, only because light was the first thing we measured moving at this speed. But we could just as easily call it the speed of causality or the speed of information. This is why faster-than-light communication is impossible. It's not that we haven't figured out how to send signals. Faster than light, it's that there is no mechanism by which one part of the universe can influence another part faster than this speed. All forces, all interactions, all information transfer is limited by this speed. Think about what this means. When you push on a wall, you feel like you're directly touching it, like there's instantaneous contact. But that's an illusion. What's really happening is that the electrons in your hand are getting close to the electrons in the wall, and they're repelling each other electromagnetically. That repulsion is mediated by virtual photons' quantum fluctuations in the electromagnetic field zipping back and forth between the electrons at light speed. The interaction feels instantaneous because light is so fast that the time delay is imperceptible, but there is a delay. Causality takes time to propagate from your hand to the wall and back. In fact, you never truly touch anything. The electromagnetic repulsion between the electrons in your hand and the electrons in the wall stops you from getting closer before actual contact occurs. Everything you've ever touched, you've only felt via electromagnetic forces propagating at light speed. Here's another mind-blowing consequence. You can never see the present. Everything you observe is in the past. When you look at your hand, you're seeing it as it was nanoseconds ago, the time it took light to travel from your hand to your eyes. When you talk to someone across the room, you're seeing them as they were nanoseconds ago, and you're hearing them as they were milliseconds ago. Sound travels much slower than light. When you look at the moon, you're seeing it as it was 1.3 seconds ago. The sun, 8 minutes and 20 seconds ago. If the sun suddenly vanished, we wouldn't know about it for 8 minutes and 20 seconds. We'd continue to see it shining, and Earth would continue to orbit the now non-existent sun for those 8 minutes, because the gravitational change would also propagate at light speed. The nearest star system, Alpha Centauri, is 4.37 light-years away. When you look at Alpha Centauri, you're literally looking over 4 years into the past. When you look at the Andromeda Galaxy, you're seeing it as it was 2.5 million years ago, when our ancestors were early hominids, just beginning to use stone tools. The cosmic microwave background radiation, the afterglow of the Big Bang that we can detect in every direction, shows us the universe as it was 13.8 billion years ago, when it was only 380,000 years old. We're literally seeing the infant universe, looking backward in time to nearly the moment of creation. This is one of the most profound implications of the speed of light being finite. The universe has a history that's visible. Because light takes time to travel, the farther we look into space, the farther back in time we see. Telescopes aren't just instruments for seeing distant places. They're time machines for observing the past. But here's something that should really make you pause. There is no universal now, because the speed of light is finite and constant. Different observers moving at different speeds literally disagree about what events are happening now in distant parts of the universe. This is the relativity of simultaneity we touched on earlier, but let me make it concrete. Imagine you're on Earth, and your friend is on a spaceship, traveling at 80% of light speed toward a distant star. You both look at that star through a telescope at what you consider to be the same moment. But because of time dilation and the relativity of simultaneity, you're literally seeing different moments in that star's history. Your now and your friend's now are different. They're not just perceiving the same moment differently, they're observing genuinely different moments in time. This gets even stranger. If your friend turned around and started traveling back toward Earth, their now would shift to include events in the star's future relative to when they were traveling away. The present moment isn't a universal thing that sweeps across the universe uniformly. It's a local, observer-dependent concept. This is why physicists often say that time is the fourth dimension, and that we live in spacetime rather than space plus time. The 3 dimensions of space and the 1 dimension of time are fundamentally intertwined. You can't cleanly separate them into space and time because the division between them depends on your motion. Here's an analogy that might help. Imagine you're standing on a flat plane and you define forward as north and sideways as east-west. Someone else standing next to you but facing northeast would have a different definition of forward and sideways. There, forward would be partly your forward and partly your sideways. Neither of you is wrong. You just have different perspectives on the same plane. Space-time is similar. You have your definition of space and time based on your motion. Someone moving relative to you has a different split between space and time. Your forward in time is partly their forward in time and partly their motion through space. The underlying four-dimensional spacetime is the same for both of you, but you're slicing it differently. And the speed of light is what determines how spacetime can be sliced. It's the conversion factor between space and time. It tells you how much distance equals how much time from different perspectives. 1 light year, the distance light travels in a year, is exactly equal to 1 year in time from light's perspective. The speed of light isn't arbitrary. It's the fundamental exchange rate between space and time. But now I need to tell you something that's going to seem paradoxical. Despite everything I've just said about the speed of light being constant, there's a sense in which light doesn't always travel at the same speed. And understanding this is crucial to understanding one of the most extreme consequences of the cosmic speed limit: black holes. Here's the setup. Einstein's special relativity tells us that the speed of light is constant in all inertial reference frames that aren't accelerating. But what about reference frames that are accelerating? What happens to light in a gravitational field? This is where general relativity comes in. Einstein spent 10 years figuring this out after special relativity, and in 1915, he published his field equations describing how mass and energy curve spacetime, and how that curvature creates what we experience as gravity. Here's Einstein's crucial insight. Gravity isn't a force pulling objects together. Gravity is the curvature of spacetime itself. Mass and energy bend spacetime, and objects moving through that curved spacetime follow curved paths that we perceive as gravitational attraction. Imagine spacetime as a rubber sheet. Place a bowling ball in the middle, and it creates a dip. A marble rolling near the bowling ball will curve toward it, not because the bowling ball is pulling on it, but because the rubber sheet is curved. The marble is following the straightest possible path through curved space, what's called a geodesic. Now here's the key point. Light also follows geodesics. Light always travels in straight lines through spacetime, but when spacetime itself is curved, those straight lines appear curved to us. This is called gravitational lensing, and we observe it all the time. Light from distant galaxies curves around massive galaxy clusters between us and them, sometimes creating multiple images or ring-like patterns called Einstein rings. But here's where things get weird. In curved spacetime, the speed of light measured locally is always constant at 299,792 kilometers per second. However, from a distant observer's perspective, light appears to slow down as it enters a gravitational field. This isn't because light is actually slowing down locally. It's because time itself is running slower in the gravitational field due to gravitational time dilation. Let me make this concrete. The GPS satellites orbiting Earth are farther from Earth's mass than we are on the surface, so they're in a weaker gravitational field. Time runs faster for them than it does for us, about 45 microseconds per day faster. If GPS didn't account for this, the system would accumulate errors of several kilometers per day. Your phone's GPS wouldn't work without Einstein's general relativity. Now, what happens if you make the gravitational field stronger and stronger? What if you compress enough mass into a small enough space that the space-time curvature becomes extreme? You get a black hole. And black holes reveal the most extreme consequence of the cosmic speed limit. A black hole is a region of space-time where gravity is so strong that the escape velocity, the speed you'd need to escape the gravitational pull, exceeds the speed of light. The boundary where the escape velocity equals light speed is called the event horizon. Inside the event horizon, even light cannot escape. Not because light is being pulled back by gravity in the traditional sense, but because space-time is so severely curved that all paths, even paths moving at light speed, lead inward toward the center. Here's the really mind-bending part. From the perspective of someone falling into a black hole, nothing unusual happens as they cross the event horizon. They don't feel any sudden change. Local physics remains the same. Light locally still travels at 299,792 kilometers per second. But from the perspective of someone watching from outside the black hole, the falling person appears to slow down as they approach the event horizon. Time dilation becomes more and more extreme, until at the event horizon itself, time appears to stop entirely. The person would appear to freeze in place, their image becoming increasingly redshifted and dimmer, fading away, but never quite crossing the horizon. Both perspectives are correct. The person falling in does cross the horizon from their perspective. It takes a finite time. But from the outside observer's perspective, it takes infinite time. The person never crosses from the outside perspective because at the event horizon, the time dilation becomes infinite. This is not just a thought experiment. In 2019, the Event Horizon Telescope collaboration produced the first image of a black hole's event horizon, or rather, the shadow cast by the event horizon on the glowing gas surrounding it in the galaxy M87. That black hole has a mass 6.5 billion times that of the Sun. The event horizon is about 40 billion kilometers across. And at that boundary, the cosmic speed limit creates a trap from which nothing, not even light, can escape. But here's what absolutely blows my mind. At the center of a black hole, general relativity predicts a singularity, a point where space-time curvature becomes infinite and the equations break down. At the singularity, our current understanding of physics fails. We need a theory of quantum gravity to understand what really happens there, and we don't have one yet. What we do know is this: once something crosses the event horizon, it must reach the singularity. This isn't a matter of having enough thrust to escape. Inside the event horizon, the singularity is in your future, the same way tomorrow is in your future. You can no more avoid falling into the singularity than you can avoid tomorrow arriving. The structure of space-time itself has been warped so severely that all futures lead inward. And the reason this trap is inescapable comes back to our cosmic speed limit, the speed of light. To escape from inside the event horizon, you'd need to move faster than light. But nothing can move faster than light, so nothing can escape. Black holes are the ultimate prison cells. Their walls constructed not of matter, but of the fundamental structure of spacetime itself, locked by the cosmic speed limit. But black holes aren't just cosmic curiosities. They're teaching us something profound about the nature of information and reality. In the 1970s, Stephen Hawking made a shocking discovery. Black holes aren't entirely black. Due to quantum effects near the event horizon, they emit radiation, now called Hawking radiation, and very, very slowly evaporate. This created a paradox. If a black hole forms from matter and then evaporates completely via Hawking radiation, what happens to all the information that was contained in that matter? The quantum states, the specific configurations of all the particles? According to quantum mechanics, information cannot be destroyed. But if it falls into a black hole that then evaporates, where does the information go? This is called the black hole information paradox, and it's one of the deepest puzzles in theoretical physics. Various solutions have been proposed. Maybe the information is encoded in the Hawking radiation. Maybe it's stored on the event horizon, like data on a hard drive. Maybe there's something fundamentally wrong with our understanding of quantum mechanics or general relativity. The current leading solution involves something called the holographic principle, which suggests that all the information in a three-dimensional volume of space can be encoded on its two-dimensional boundary. This has mind-blowing implications for the nature of reality itself. It suggests that our three-dimensional universe might be a kind of hologram, a projection of information encoded on a distant two-dimensional surface. And all of this the black hole information paradox, the holographic principle, the very existence of event horizons, ultimately traces back to the cosmic speed limit. The speed of light isn't just a speed. It's a fundamental feature of how information can exist and propagate in our universe. Now, at this point, you might be feeling overwhelmed. We've journeyed from simple questions about why light moves at a certain speed to the nature of spacetime itself, from the expanding universe to the information paradox. But I want to bring things back down to Earth for a moment and talk about how this cosmic speed limit affects your daily life in ways you probably never realized. Because here's the thing, the speed of light might seem like a distant, abstract concept that only matters to physicists and astronauts. But it's actually shaping your experience of reality right now, at this very moment. And understanding this is going to change how you think about consciousness, perception, and what it means to exist in this universe. Are you ready to discover how the cosmic speed limit is affecting you personally, right now? Let's talk about you. Right now, this moment, the present instant of your conscious experience. Except there's a problem. The present instant doesn't exist the way you think it does. Your consciousness, your subjective experience of the now, is actually a carefully constructed illusion, stitched together from signals that arrived at different times, all limited by the speed of light. Here's what I mean. Right now, you're probably seeing this text, maybe hearing audio, perhaps feeling the device in your hand. You experience all of these sensations as happening simultaneously in the same now. But they're not. They're all arriving at your brain at different times, via signals traveling at different speeds. And your brain is working incredibly hard to synchronize them so that they feel simultaneous. Light from your screen hits your retina. This triggers electrochemical signals that travel down your optic nerve at about 100 meters per second less than 1/1,000,000th the speed of light. These signals reach your visual cortex, where they're processed. Meanwhile, if there's audio, sound waves travel through the air at about 343 meters per second, hit your eardrum, and trigger electrochemical signals that travel to your auditory cortex. If you're holding a device, pressure sensors in your skin send touch signals to your somatosensory cortex. All of these signals arrive at different parts of your brain at different times. Visual information takes about 8/100 milliseconds to reach conscious awareness after hitting your retina. Auditory information takes about 40 to 50 milliseconds. Touch information takes about 50 to 80 milliseconds, depending on where on your body the touch occurs. Your brain has to solve what's called the temporal binding problem, how to create a unified, synchronized experience of reality from all these asynchronous inputs. And it does this by ... cheating. Your brain essentially predicts what should be happening now based on the signals it received in the recent past, and it presents this prediction to your conscious awareness as the present moment. You're not experiencing reality in real time. You're experiencing a carefully constructed model of reality, delayed and smoothed out so that it feels coherent. Your consciousness lives about 80 milliseconds in the past, watching a recording while believing it's live. This is wild enough, but here's where the speed of light comes in. Every single signal your brain is processing started as electromagnetic interactions propagating at or below the speed of light. The photons hitting your retina traveled from their source at light speed. The electrons carrying signals in your neurons are pushed along by electromagnetic forces that propagate at light speed. Even the chemical neurotransmitters that cross synapses, the gaps between neurons, are driven by electromagnetic interactions. Your thoughts themselves are subject to the cosmic speed limit. When you have an idea, when you make a decision, when you feel an emotion, these mental events are physical processes occurring in your brain, mediated by electromagnetic forces, constrained by the speed of light. Now you might object, but my brain is only about 15 centimeters across. Light crosses that distance in about 0.5 nanoseconds. Why would the speed of light matter at that scale? You're right that pure light speed delays across your brain are negligible, but the electrochemical signals in your neurons travel much slower than light, about 100 meters per second for the fastest neurons, down to about 1 meter per second for the slowest. This means signals can take up to 150 milliseconds to cross your brain. And this delay matters. There are documented cases where the speed of neural signaling creates perceptible effects. For example, when you stub your toe, you feel the impact after a noticeable delay, sometimes a full second or more, because the pain signal has to travel from your toe all the way up your spine to your brain. Your brain actually registers the visual information of stubbing your toe before it registers the pain. You see yourself stub your toe, and then a beat later, you feel it. Here's an even stranger consequence. Different parts of your body are essentially living at different points in your subjective timeline. When something touches your nose and your toe simultaneously, your brain receives the signal from your nose tens of milliseconds before the signal from your toe. To maintain the illusion of simultaneity, your brain has to adjust its processing, delaying the nose signal so that both seem to arrive at the same time in your conscious experience. This gets really weird when you consider what happens during rapid events. Imagine you see a flash of light and hear a sound at the same instant. If the light and sound were actually produced simultaneously some distance away, you'd see the light first and hear the sound later because light travels faster than sound. Your brain knows this, and it actually adjusts your perception so that if the light and sound arrive with the expected delay, you perceive them as simultaneous. But if the light and sound are produced right in front of you close enough that sound delay is negligible, your brain still makes this adjustment, which means you actually perceive the sound as happening slightly before the light, even though both stimuli hit your sense organs at roughly the same time. Your conscious experience is not a passive recording of reality. It's an active, predictive model adjusted for propagation delays. Now let's zoom out a bit. The speed of light doesn't just affect your individual consciousness, it affects social reality. Every conversation you have is mediated by signals traveling at or below the speed of light. When you're talking to someone in person, you're seeing them as they were nanoseconds ago and hearing them as they were milliseconds ago. Your brain synchronizes these inputs so smoothly that you don't notice the delay. But when you make a video call to someone on the other side of the world, the delays become noticeable. Light takes about 67 milliseconds to travel halfway around Earth. Add in the time for signals to be encoded, transmitted through fiber optic cables or satellites, and decoded, and you're looking at delays of 150 to 300 milliseconds or more. This is why video calls feel slightly awkward. The normal flow of conversation is disrupted by the finite speed of light. For astronauts on the International Space Station, communicating with mission control involves a delay of only a few milliseconds, negligible. But for astronauts on the moon, there's a 2.5-second round-trip delay. Every question takes 1.25 seconds to reach Earth, and every answer takes 1.25 seconds to return. Conversations become stilted, more like exchanging messages than real-time dialogue. For future Mars missions, this gets much worse. Mars is between 4 and 24 light minutes away from Earth, depending on orbital positions. At best, a question sent from Mars takes 4 minutes to reach Earth, and the answer takes another 4 minutes to return an 8-minute round trip. At worst, it's 48 minutes. Real-time conversations become impossible. Mars colonists will be isolated not just by distance, but by the fundamental structure of spacetime itself. This has profound implications for any future interstellar civilization. If humanity ever spreads to other star systems, a big if, given everything we've discussed about the difficulty of interstellar travel, the speed of light will enforce a kind of cosmic censorship. Different star systems will be separated by years or decades of communication delay. Imagine humanity has colonies around Alpha Centauri, 4.37 light-years away. Earth sends a message. We've made a breakthrough in fusion power. The message arrives 4.37 years later. Alpha Centauri responds, "Amazing! Here's our refinement of your design." That response arrives on Earth 4.37 years after that. A single back-and-forth exchange, takes nearly 9 years. By the time Earth receives Alpha Centauri's response, the breakthrough might be obsolete, superseded by newer developments. The two civilizations would drift apart, evolving independently, unable to maintain the kind of real-time cultural exchange that keeps societies unified. After a few generations, they might barely recognize each other as the same civilization. This is one of the solutions to the Fermi paradox, the question of why, if the universe is teeming with life, we haven't detected any signs of alien civilizations. Maybe advanced civilizations exist, but they're scattered across vast distances, separated by communication delays of years, centuries, or millennia. Maybe the speed of light makes galaxy-spanning empires impractical, fragmenting civilizations into isolated clusters. Or maybe, and this is what really keeps me up at night, maybe the speed of light isn't just a practical limitation. Maybe it's a fundamental filter. Maybe the universe is structured this way deliberately, if you can even apply that word to physical laws. Maybe the cosmic speed limit isn't a bug. It's a feature. Think about it. If information could travel instantaneously, if cause and effect could propagate infinitely fast, the universe would be a very different place. Causality would be instantaneous and universal. There would be no delay, no light speed lag, no buffer between action and consequence. Every event would instantaneously affect every other event everywhere. Such a universe might be inherently unstable. It might not be able to support complex structures like stars, planets, or life. The speed of light might be necessary for the universe to have the structure it does, for it to have a well-defined arrow of time, for cause and effect to work, for localized complexity to emerge. In other words, the cosmic speed limit might be one of the fundamental parameters that make the universe habitable. Change it, and you might not get a universe that's merely different. You might not get a coherent universe at all. This leads us into deep philosophical territory. Why does the universe have the constants it does? Why is the speed of light 299,792,458 meters per second and not some other value? Why do the laws of physics have the form they do? These are questions at the boundary of physics and philosophy. Some physicists argue that the constants are arbitrary. They just happen to have the values they do, and we exist to observe them, because if they were different, we wouldn't be here to ask the question. This is called the anthropic principle. Others suggest that there might be a deeper explanation, perhaps a more fundamental theory that explains why the constants have the values they do. String theory, for instance, predicts that our universe might be one of an enormous number of possible universes with different physical constants, all existing in some vast multiverse. The speed of light has its value because that's the value it happens to have in our particular universe. But these are speculations, far beyond what we can currently test experimentally. What we know for certain is this: the speed of light is a fundamental constant of our universe. It defines the maximum rate at which cause can propagate to effect, and it shapes everything from the structure of space-time to the nature of consciousness to the fate of civilizations. And now, after this long journey through relativity, black holes, cosmic horizons, and the nature of consciousness, I want to bring us to the most profound implication of all. Because the cosmic speed limit doesn't just constrain what we can do or know, it defines what we are. And understanding this is going to reframe everything we've discussed. Ready for the final revelation? Let's talk about what the speed of light tells us about the fundamental nature of reality itself. Everything we've discussed, time dilation, length contraction, black holes, cosmic horizons, the limits on consciousness, all of it stems from one simple fact: the speed of light is constant in all reference frames. But why? Why should the universe work this way? Most of the physical constants we know about, the mass of an electron, the strength of gravity, the charge of a proton, these seem arbitrary. They're measured values that we plug into our equations. We don't know why they have the values they do. They just do. But the speed of light is different. The speed of light isn't arbitrary. It's not a property of light per se. It's a conversion factor. It converts space into time and time into space. It tells us how space-time is structured. In fact, many physicists prefer to work in units where the speed of light equals 1. In these natural units, measuring distance in light seconds or light years, the speed of light disappears from the equations entirely. It's not that light travels at 1 light year per year. That's tautological. It's that space and time are fundamentally the same kind of thing, measured in the same units. And the speed of light is just the conversion factor we need because we stubbornly insist on measuring space in meters and time in seconds. Think of it this way. Imagine someone told you that there was a conversion speed between northward and eastward motion. That sounds absurd, right? North and east are both directions in space. There's no fundamental difference between them except your orientation. You don't need a conversion factor. But now imagine you lived in a universe where you could only perceive one spatial dimension at a time, and you measured northward distance in meters, but eastward distance in, I don't know, fidgets, some arbitrary unit. Then you'd need a conversion factor to translate between meters north and fidgets east. But that conversion factor wouldn't tell you anything fundamental about space. It would just be an artifact of your measurement system. The speed of light is like that. It's telling us that space and time are aspects of the same thing, space-time, but we measure them in different units, so we need a conversion factor. The fact that this conversion factor has a specific, finite value is what creates all the weird relativistic effects we've been discussing. But here's the deeper question. Why is space-time structured this way at all? Why does the universe have this geometry where space and time are interchangeable aspects of a four-dimensional manifold? This is where we reach the edge of current physics and step into speculation. But there are some fascinating hints about where the answer might lie, and they all point towards something profound. The structure of space-time might emerge from something more fundamental. One of the leading candidates for this more fundamental thing is quantum information. Several approaches to quantum gravity, including loop quantum gravity, string theory, and especially something called the holographic principle, suggest that space-time isn't fundamental. It's emergent. It arises from a more basic substrate of quantum information. Think of it like this. Temperature isn't fundamental. Temperature is an emergent property that arises from the average kinetic energy of molecules. You can't point to a single molecule and ask what its temperature is. Temperature only makes sense when you're talking about large collections of molecules. Similarly, space-time might be an emergent property that arises from the collective behavior of quantum information. In this view, the speed of light would be the emergent speed at which correlations can propagate through the network of quantum information that underlies reality. It's the maximum rate at which one bit of quantum information can influence another bit, and this rate defines the structure of emergent spacetime. This is mind-blowing because it suggests that space and time aren't real in the way we think they are. They're convenient descriptions of a deeper reality, like how temperature is a convenient description of molecular motion. The cosmic speed limit isn't a law imposed on reality from outside. It's a consequence of what reality fundamentally is. Let me give you an analogy. Imagine you're playing a video game, a massively multiplayer online game with thousands of players. In the game world, there are rules. You can't walk through walls. You can't teleport across the map. Things fall when you drop them. These rules feel real within the game. They constrain what you can do. But from outside the game, we know these rules are just programming. They're algorithms running on a computer server. The world of the game is just data structures, numbers in computer memory representing positions, velocities, inventories. The rules are just checks the program performs to maintain consistency. Now, what if our universe is similar? Not literally a computer simulation. That's probably too anthropomorphic a metaphor, but something where the rules we experience as physical laws are emergent from a more fundamental computational or information theoretic substrate. In such a universe, the speed of light might be analogous to the maximum update rate of the underlying system. Just like a video game has a tick rate, a maximum frequency at which the game state can update, the universe might have a fundamental maximum rate at which information can propagate. That rate is what we experience as the speed of light. This isn't just wild speculation. There's serious research into this. The holographic principle, for instance, suggests that the information content of any region of space is proportional not to its volume, but to its surface area. This implies a maximum information density for any region of space, which in turn implies limits on how much can happen in that region in a given time, limits that are related to the speed of light. The physicist John Wheeler, who coined the term black hole and mentored many leading physicists, famously proposed it from bit, the idea that physical reality, it emerges from information. Bit. In his view, every particle, every field, every force is ultimately a manifestation of quantum information. If this is true, and we're still far from proving it, then the speed of light isn't just a speed limit. It's the frame rate of reality. It's the fundamental clock speed of existence. And here's what absolutely blows my mind about this. If space-time emerges from quantum information, then everything we've discussed, time dilation, black holes, cosmic horizons, the impossibility of faster-than-light travel, it is a consequence of information theory. The structure of reality is determined by the mathematics of information. This has profound implications. It means that the universe is, in some deep sense, comprehensible. The laws of physics aren't arbitrary edicts handed down by some cosmic lawgiver. They're mathematical necessities that emerge from the structure of information itself. It means that an intelligent being anywhere in the universe, studying its local physics, would eventually derive the same mathematical structures we've discovered. Special relativity, general relativity, quantum mechanics. These aren't just human constructs. They're descriptions of universal patterns that emerge from the nature of information. And it means that you, yes, you, watching this right now, are a pattern of information. Your consciousness, your memories, your identity, these are all information patterns encoded in the physical substrate of your brain. When you learn something, you're reconfiguring information patterns. When you make a decision, you're computing an output from information inputs. This doesn't make you less real or less significant. If anything, it makes you more miraculous. You're a self-sustaining pattern of information complex enough to be aware of itself. You're information that knows it's information. You're the universe examining itself. And the cosmic speed limit, the speed of light, is the fundamental rate at which the information that is, you can interact with the information that is the rest of the universe. It's the speed at which you can affect the world and the world can affect you. It's the bandwidth of your connection to reality. Now, I want to address something that might be bothering you. Throughout this video, I've talked about the speed of light as a limit, a constraint, a barrier. I've painted it as something that traps us, that prevents us from exploring the cosmos, that isolates us from distant civilizations. But here's a different perspective. Maybe the cosmic speed limit isn't a limitation. Maybe it's a liberation. Think about it. If information could propagate instantaneously, if every event everywhere immediately affected every other event, you couldn't exist. There could be no isolated systems, no local structures, no pockets of order in the cosmic chaos. The speed of light creates a kind of cosmic isolation, a buffer zone around every point in space where local conditions dominate over distant influences. This isolation is what allows complex structures to form and persist. It's what allows stars to maintain themselves against the background radiation of the cosmos. It's what allows planets to develop unique environments. It's what allows life to evolve independently in different locations. It's what allows you to have a coherent identity separate from the rest of the universe. The speed of light doesn't trap you. It defines you. It creates the boundary between you and not you. Without this fundamental maximum rate at which information can propagate, the distinction between yourself and the environment would dissolve. You'd be smeared across the universe, indistinguishable from the background noise. In other words, the cosmic speed limit is necessary for individuality, for identity, for the very possibility of distinct entities existing. It's not a bug. It's a feature. It's not a limitation on what you are. It's a definition of what you are. And here's the beautiful, empowering truth that emerges from all of this. You are a localized pattern of causality. You are a node in the causal network of the universe, processing information and generating outputs, all at rates constrained by the fundamental speed of causality, the speed of light. Every decision you make ripples outward at light speed, affecting your environment, which affects other people, which affects the broader world. You are constantly broadcasting your influence into the future light cone, the region of spacetime that can be causally affected by your present actions. You can't affect the past. You can't affect events outside your light cone. But within your light cone, within the region of spacetime that can be reached by signals traveling at or below light speed from your present location, you have influence. You matter. You make a difference. And that difference propagates into the future, at light speed and below, creating ripples in the causal structure of the universe that will persist long after you're gone. Some of those ripples, photons you've reflected, gravitational waves you've contributed to, information you've shared, will continue outward, potentially forever, limited only by the expansion of space and the heat death of the universe billions of years in the future. You are not just in the universe. You are part of how the universe processes information, part of how it evolves, part of how causality propagates. And the speed of light, this fundamental cosmic constant we've spent hours exploring, is the rate at which your influence spreads, the rate at which you can affect reality, the rate at which you participate in the unfolding of existence. So yes, the speed of light limits how fast you can travel. It constrains where you can go and what you can know. It isolates you from distant parts of the universe. But it also protects you. It gives you space to exist as a distinct individual. It gives you time to process information, to make decisions, to live a coherent life. It creates the structure of causality that allows the universe and you to have a meaningful history and a meaningful future. The cosmic speed limit isn't a wall keeping you trapped. It's the framework that allows you to exist at all. Now, as we come to the end of this journey, I want you to pause for a moment and reflect on what we've covered. We started with a simple question. Why is the speed of light the ultimate limit? And we've discovered that the answer involves the very nature of space, time, causality, information, and existence itself. We've learned that time is relative, that simultaneity is observer-dependent, that mass increases with velocity, that space can expand faster than light, that black holes trap even light itself, that consciousness operates with signal delays, that civilizations are isolated by cosmic horizons, and that reality itself might emerge from quantum information. All of it, traces back to one simple fact. The speed of light is constant in all reference frames. That single constraint generates all the strange, wonderful, mind-bending features of our universe. And here's my final thought, the thing I want you to take away from this video. You live in a universe governed by deep mathematical principles. These principles aren't arbitrary. They emerge from the structure of information and causality. And because of this, the universe is comprehensible. It can be understood. It can be explored, not just with our eyes and hands, but with our minds. You right now understand something profound about reality. You understand why there's a cosmic speed limit, what it means, and why it matters. You followed a chain of reasoning from everyday experience to the deepest questions about the nature of existence. And that ability, the ability to understand, to reason, to discover truth, is itself a consequence of the universe's lawful structure. The speed of light might limit how fast you can travel through space, but it doesn't limit how far you can travel through understanding. And in the end, that might be the most important journey of all. Thank you for joining me on this journey through space-time. If this video expanded your mind, if it made you see the universe differently, do me a favor. Hit that like button, subscribe for more deep dives into the nature of reality, and share this with someone whose mind you'd like to blow. Drop a comment telling me which part of this journey was most mind-bending for you. Was it time dilation? Black holes? The idea that space and time are the same thing? Or maybe the realization that you're a pattern of information propagating at the cosmic speed limit. And remember, every photon you see, every signal your brain processes, every decision you make is part of the vast causal network of the universe, limited by the speed of light, but unbounded in its significance. Until next time, keep exploring, keep questioning, and never stop wondering about the magnificent, mysterious, mathematically beautiful universe we're privileged to inhabit.